Hey everybody, welcome back to our course on data structures and algorithms. I want to talk today about some more sorting of arrays. I want to look at the algorithm Quicksort. So I have a Quicksort viewer and I'd like you to download it. If you go to any search engine and just search my name, Jed Wilshire, you should see it come up. And it's usually that first link there. And here under computer science, you can go to advanced computer science. And what I'm looking for is right there, the Quicksort viewer. So you just click on that and then download it. I can click download to my documents, or download to wherever you want to save it. I'll just save it to my downloads, and you see I've already got it there actually. Now after doing that, if you go to edit, add class from file, you can go where you saved it and pull it in. And here it is, Quicksort viewer. As you can see, I've already done all that ahead of time. Just run the application. And I want to take learning Quicksort in 2 steps. Okay, this is a tough algorithm, but we can do it. First step I want you to get is a general feel for why it works. And it's not that hard an algorithm to understand why it works. It's just a little bit tricky to actually implement. So let's start by just running the application. And I'll hit shuffle. Yours likely look different than mine. I want to get a nice pivot value. Okay. So what we're going to do is Quicksort's going to start with a partition that is the entire array. So we're starting with this entire array of numbers, and we're going to use the traditional Quicksort that picks a pivot from the very far left. So in this case, my pivot is indicated in red. It's the number 10. And what we're going to do essentially is move all the values that are less than 10 to the left of it, and all the values that are greater than 10 to the right of it. Okay? And, we'll have to handle ties and things like that. And that's just part of what makes this algorithm a little bit tricky to implement. So you can see after moving everything across the pivot, all the numbers 7 through 9 are on the left-hand side of that 10. And all the numbers 11 up through 16 are on the right. So if I notice, these numbers on the left are not in order, the numbers on the right are not in order, but I know that since every number less than 10 is to its left, every number greater than 10 is to its right, the 10 has got to be sorted. So I'm going to declare that sorted and box it with I'm boxing it in black, indicated we're done with it. So we've now divided this our partition that was the entire array into 2 sides, a left and a right. And in Quicksort, we're going to recursively call Quicksort on the left and then on the right. So we're going to keep sorting, cutting these partitions in the smaller and smaller chunks and sorting them going to the left, and then we'll come back and finish up on the right. So I'll go to the left of the 10. So I'm now sorting just 7 through 8. I'll pick this pivot here. It highlights my pivot value of 7. I'm going to move everything less than 7 to the left. You can see I've got a 9 and an 8 over here, and then a 2, 5, etc. over here, but the 7's done. All right, let's call Quicksort on the left again, this time on the left of the partition from 2, all the numbers 1 through 9 were one partition. Now we're going even further. So we're going to do these numbers over here, these 6 numbers less than 7. I pick a 2, and I move everything across it. The 2 is now sorted. Notice I've also indicated the 1 is sorted. That's because the partition to the left of the 2 was only one size. If we have a partition that has only got 1 number in it or no numbers in it, we're going to call that partition done. And you'll see how that's where we're going to stop our recursion. And if you think about it, if I have an array of just 1 number, isn't it accurate to say that I've sorted it from least to greatest? So we're going to call that 1 is sorted. Notice it now gives me the option to sort on the right. Because we've sorted to the left of the 2, now I'm going to sort to the right of the 2. I pick a pivot, and I move. Well, not much happened there. Quicksort on the right of the 3, because the left was already done. Pick a pivot, move across the pivot, and now we're all the way up to here. Now I'm to the right of the 7. See, we're slowly coming back. We're still working on the left-hand side of that original pivot of 10. We're finally back to the original pivot of 10, and I'm now calling quicksort on the right of it. I pick a pivot, 16, not a great pivot, but that'll work, and move everything over here. To the left of 16 gives me the 14 as my pivot. Move everything to the left of 14. And keep going. What I want y'all to do, download the application, run it in BlueJ until you get a feeling for how it works. So I want you to pause the video whenever you're ready, play with it, get a feeling for how it works, and then restart the video when you're ready to really analyze it. Okay, welcome back. I have an array here that I'm going to use, and I've got the steps of my algorithm, and I'm trying to use some color here to kind of make it clear. You'll see why in a minute. So, actually, I'm going to highlight. Let's highlight these cells like I don't know, like a light pinkish color. Okay, and we'll do that. Now, more colors. There we go. Okay, so. Let me shuffle here, and yours will probably look different than mine, but we can just follow along with mine for now. I want to have 8 on the left because I want my first pivot to be a nice pivot. Okay, so I'm going to pick a pivot, and before I click move across, I want to see if we can't predict what's going to happen. So let's run through this. So my pivot value, according to our algorithm, whenever we call a partition, we set the pivot as the first element in the partition. So this is going to be my pivot right here. I'm going to indicate it's a pivot by highlighting it that. I'm going to let L be this value here. And that's step 2. I'm going to let R be this value here. So you could let L be the index of the pivot. It's going to turn out that it's always going to move up 1 at least. So my L is going to start 1 to the right of my pivot, and my R is going to be all the way at the right-hand side of my partition. Right now we're dealing with the entire array as our partition, okay? Now, this part here in yellow that we're about to enter, we're going to keep doing that over and over and over again as long as L is less than or equal to R. So what we're looking for is we're looking to get that L to the right of the R. Once that's done, then we're ready to move on. We've got to get the L to the right of the R, not equal, but beyond it. So move L up as long as that element is smaller or equal to the pivot and in bounds. You need to be careful. Always check your bounds in an array or sorting before you start accessing. But we'll get to that when we're coding it. All right, so, oh, you know what? I need to make my array look like the one on my screen. Okay, there we go. So now it matches what I have up here, right? We should be able to get the exact same results as the computer program if we do this right. So I need to move L up as long as that element is smaller than or equal to the pivot. 3 is smaller than 8, so move L up. 1 is smaller than 8. 2 is smaller than 8. Smaller or equal, technically. 15 is not. Stop there. We found the L that we need to swap. And that's what we're looking to do. We're looking to find a value on the left-hand side of where our pivot should be that needs to swap with a value that's too big on the right. We're going to kind of fix 2 problems at once. We're going to find a bad value on the left, a bad value on the right, swap both of them, and now we fixed both problems. Okay, R needs to, that was step 4, to find the L. Step 5 is to find where to put R. Move R down as long as that element is greater than the pivot. Strictly greater, not greater than or equal to. Well, 5 is not greater, so we stop. Okay, if L is lower than R, we're going to swap these elements. So I'm going to swap 5 and 15. And then move L up. We're going to do all this whenever L is less than R. Move R down. All right. And we're going to go back to step 4 as long as L is less than or equal to R. So we keep doing steps 4 through 6 as long as L is less than or equal to R. and I'll just continue using this. I'm using this Excel spreadsheet because I like it. It allows me to shift things around and move numbers. It's a good way to practice sorting algorithms. Okay, so 12. We're going to move L. We're back at step 4. Move L up as long as that element is smaller than or equal to the pivot. 12 is not smaller than 8, so L stays where it is. Step 5. Move R down as long as that element is greater than the pivot. Well, 13 is greater than the pivot. 16 is greater than the pivot. 10 is greater than the pivot. Remember, my pivot is 8. 4 is not. Okay, so we stop moving L and R. If L is lower than R, we swap these values. So 4 goes here. 12 goes here. Move L up. Move R down. L is less than or equal to R. We go back. Let's keep going. All right. Back to step 4. Move L up as long as that element is smaller than or equal to the pivot. Okay, I don't move L then. R. Move R, step 5. Move R down as long as that element is greater than the pivot. 7 is not greater than the pivot, so I don't move them. I need to swap them. 7 goes here. 9 goes here. You know the drill. Move up L. Move down R. Okay, go back to step 4. If L is less than or equal to R, we're back at step 4. Move L up as long as that value is less than or equal to pivot. 6 is less than or equal to 8, but 14 is not. Okay, so we stop moving L. Now move R down as long as that element is greater than the pivot. 11 is greater than 8. 14 is greater than 8. 6 is not greater than 8. Okay, step 6. If L is lower than R, it's not. It's not lower than R. So I don't need to do anything here. All right, so we move down to the next step. We're going to swap the pivot value with the value at the index of L minus 1. All right, so this is really important that we understand this. So the whole purpose of that, looping through steps 4, 5, and 6 was to get everything less than or equal to 8 on one side and everything greater than 8 on the other. The way that this is set up, L is indicating the index of the first value that is bigger than 8. So if I swap the value 8 with the value behind L, I should be swapping a value that is not bigger than 8. So I won't violate that partition rule. So let's put 6 here and 8 there. So that's that all-important final step, is putting that pivot in its right place. And it absolutely must be sorted now, right? We moved everything smaller than 8 to the left, everything bigger than 8 to the right, so 8 must be in the right place. Makes sense, I hope. But that step 7 is so tricky. You have to be really careful with how your L's and R's move and end up. You'll notice the way I'm doing this algorithm, we're going to be swapping L and moving L up and down. Step 6 only occurs if L is less than R, right? But we repeat as long as L is less than or equal to R. Okay, so in fact, I should probably move this over here because that's kind of his own thing. It's the loop condition, and we'll see that in the code when we do it. All right, so 8 sorted. Recursively call back to step 1 with the left and right hand side to the pivot. So we're going to sort this side now. We're going to call, but we need to figure out what that is. So we're going to recursively call back to step 1. So L is under the 14, right? It's index 0, 1, 2, 3, 4, 5, 6, 7, 8, it looks like. So 8 went in right here at index 7, but 8 is sorted. Everything up to L minus 2 still needs to be sorted. So we're going to recall back to L minus 2, all right? And that starts the whole procedure over again. When we get back to calling on the right, we'll call from L up to the end of the right-hand partition. So we're going to put L there. We're going to mark that as our pivot. We're going to put R here. The 8's already sorted. It's not part of a partition. Move. We're back here, and that's taken care of. Step 1, 2, 3. Step 4, move L up as long as it's less than or equal to pivot. It's going to move L, well, all the way up to here where R is. I'll move R down. Okay. R is going to move down as long as that element is greater than pivot. So R is going to move down to here. So it turns out that L is not lower than R. We don't swap them. I don't move anything. I just need to go right here to swap the pivot value with the value at L minus 1. So this becomes a 4. This becomes a 6. And it's done. So the 6 is now been sorted. The pivot value is the one that's been sorted. So now I'm going to call quicksort on the left over here. Okay? So I'm calling it on the left. So this becomes my pivot. This will be L. This will be R, right? Because we called it on this side of the 6. 3 is less than 4. We're going to move L all the way up to there. R is going to move down. And now we can see that L is not less than R, so we're going to swap 2. 2 is going to go there, and 4 is going to go there. You know, I meant to review, checking our work. What I want you to do is to do the algorithm just like I am with pencil and paper or Excel spreadsheet or whatever, and check. We should see exactly what we had before. We had the 8, and then we had all those values. Call quicksort on the left, pick a pivot. The 6 should move next to that spot. Quicksort on the left, the 4 is going to pick, and the 2 is going to go there. You can see that we have 2, 3, 1, 4, 5, 6, 7, 8, and this side is fine. All right, let's just do a couple more for practice. We just sorted the 4. So we'll call quicksort on the left. The 2 is going to be our pivot. 3 is not less than or equal to 2. R is not greater than or equal to 1. So steps 4 and 5 are done. We're going to flip-flop L and R because L is less than R. That becomes a 1. That becomes a 3. L goes up. R goes down. L is no longer less than or equal to R. So we have found the right place for our pivot. Put a 1 here and a 2 there. Because we're swapping our pivot with the position. Remember, put the pivot in, swap it in with the point right behind where L ends up. And so that means that my pivot was the 2, right? All right, so let's talk about it. When I call quicksort, now on the left of this 2, that's an array of size 1, or a partition of size 1. It must be sorted. Then we come back, we call it on the right of the 2. That's a size 1. Then the 4 comes back. That's a size 1. The 6, we came back to that. It's a size 1. And finally, at this point, we're back where we started, calling to the right of the 8. And we can watch the computer do this as well for us to make sure we did it correctly. And you can see it, once it gets down to size 1, it just cruises right through them. Quicksort on the right, pick a pivot, and I'll let you go on and see what you get for that. You can pause the video at this time and try and do the work. Okay, let's see if you did the next step correct. All right, let's call quicksort on the left. So we're doing the 13, 11, 9, 12, and 10. Pick a pivot. All right, pause the video. Let's see how you did. 10, 11, 9, 12. Quicksort on the left of the 13. Pick a pivot, the 10. And from here, I think you pretty much got the idea. It's pretty much done now. And that's it. Okay, let's see how we would code this. All right, here is our quicksort algorithms kind of framework. I'd like you to start with a class like this. I'm using static methods that will make it easier for us to call and test them. So I've got my public static void quicksort, which takes in an array, and this is the array that it will sort. anything done to an array parameter is permanent. So if a user calls quicksort and sends me an unsorted array, I don't have to send them something back. I don't need to return to them a sorted array. That array they sent is now sorted because it's called passing by reference. If you want to, you can look that up. We could talk more about that at a later time. All right, so I'm just going to make explicit here that I'm going to call a recursive method where starting with the left side of my partition at index 0, the right side at the last index of my array. And notice that that method is private. I don't want my users trying to call it. There's a lot of thought that goes into what left end and right end is and how the partitions are. I don't want them trying to figure that out. They just call quicksort, we handle the rest. Okay, let's take a look at the recursive quicksort method. We got to have a way to stop calling quicksort. So we're going to stop quicksort when you send it an array where the left end and the right end are the same value, meaning that they're both the same index, so you have an array partition of only size 1. If I've got a partition of size 1, it's already sorted. But also, I could have the left end called to the right of the right end. I could have an array of size 0, so a partition of size 0. So we want to check either that right end is less than or equal to left end, or that their difference is less than or equal to 0. But keep in mind there's two possibilities there, that the right and left end could be equal, or they could actually be kind of on the wrong side of each other. If they are, just return. Don't do any more. Don't go any further down in the recursion chain. Okay. Well, I'm going to create some variable names here. I recommend you use these. I got pivot index is the left end. So again, in the traditional quicksort, we're going to pick a pivot from the whole left-hand side of the partition every time. There is some modified quicksorts that pick a pivot a little differently, but we're not discussing that today. All right, I'm going to start with my left value, L at left end plus 1, so just to the right of my pivot, and R is at my far right end of my partition. The first time this is called, those will be index 0 and index length minus 1, but for subsequent calls, it will not be the same. All right, we're going to do those steps 4, 5, and 6 as long as L is less than or equal to R. We need to get that L past the R. Once that L goes past the R, right behind it, that's where we're going to drop in our pivot, right? So, try and code in 7 and 8 and using these steps here, okay? So I took care of the stopping the recursion. You just need to, I took care of, let's see here, step 1, 2, and 3 are here. You need to code this in, okay? I took care of the go back to step 4, right? We got that already in the while loop. You need to do step 4, 5, and 6. Steps 4 and 5 are about moving something until something is no longer true. So think about what that would be. Step 7, that's where we insert it right behind L. And then on step 8, I want you to recursively call from the left and right hand sides of the pivot. When we sorted earlier, the first thing we sorted was this 8. Let me get rid of this color right quick. When we first sorted that 8, we had to, this was L, if you recall. This is L minus 1. When we recursively call quicksort recursion, I need you to give it partitions from the left end up to L minus, not 1, that's 8, but L minus 2. Then the right side is from L all the way to the end. Okay? Give it a try right now, and then pause the video. We'll come back in a couple minutes, and we'll go over your answers. All right, let's see how you did. Step 4, move L up as long as that element is smaller than or equal to the pivot and in bounds. So while L is less than or equal to the right end, that it can be equal to the right end, that's in our partition, but it just can't be past it, and array bracket L is less than or equal to the pivot value, which is an array pivot index, move L up. While R, step 5, That's step 4. Step 5, while R is greater than or equal to the left end and array bracket R is strictly greater than the array at pivot index, let's decrease R. All right, so at that point we found our L and R values. If L is still less than R, then what I want to do is swap them. So I've got a method here, a swap method that I wrote. Again, it's private, and I'll just call it with the array values, my array, and the indexes that I want to swap. I want to swap L with R. All right. Then L moves up 1, R moves down 1, and that's it. Okay, well that was step 6, right? Okay, so hopefully you've got something similar to that. You know, I want you to understand the process. It doesn't have to be absolutely perfect, though. These are tough. There's lots of little things. You know, a misplaced equal sign or, you know, not having quite the right numbers can really cause issues. You just have to debug sometimes. It's hard to write this one absolutely perfect from scratch. All right, step 7. Let's go back and look at that. Swap the pivot value with the value at index L minus 1. So remember, the way we have this set up, by the time we're done with that while L is less than or equal to R loop, that L is going to be at a position 1 greater than where that pivot needs to be. So we're going to swap. So I'll use my swap method that takes an array. We're going to swap index L minus 1 with the pivot index. Okay? Step 8, we're going to recursively call on the left, on the right. So I'm going to call this is called quick sort rec with my array. The left-hand side is the left end of, so you have to picture, we have a partition. We just found this perfect spot right here, somewhere in the middle-ish. We're going to call all the way up to that. From the left all the way up to that. So left end up to L minus 2. Remember, L is actually at the position to the right of where we inserted our pivot, right? We found that perfect value. We put the pivot right here at L minus 1. So I need to go all the way up to L minus 2. The other side, I'm going from L to the right end. Okay? And that should work. Let's see how to test it. Okay, so let's make an array. And right here, I'm just going to use this kind of workbench area where we can an interactive shell. So I'll say new int square brackets, but I won't put the size, and I'm giving an initializer list. And I want to use lots of different numbers. I really want to check all sorts of different things to make sure we have everything handled. Let's make sure you use some negative numbers, some bigger numbers, 0, also some repeat values, because if we have a little bug in our code, it could mess up with when there's 2 of the same number. And if you don't put a semicolon on it, it'll appear on our workbench here. Try that again there. There it is. Okay. And I'll just call this R. Okay, so if I double click on it, it should allow me to inspect it. It's got a length of 13. Those are the numbers, and I put them in that order. They are definitely not sorted. Quick sort test. Remember, we only had one public method. Click on that. And click on the array that you want sorted, and let's check it out. Looks pretty good, doesn't it? Well, that's it. That's quick sort. It's a tough one. It's a tough one to get absolutely right, just cold. But it's an important algorithm. Why? Because, well, it's quick. And the ON of quicksort is very fast, and it's average case scenario. Yeah, it looks like there's a lot of loops in here, doesn't it? But remember, these while loops here are quite short. They are being cut down in half every time. So we've got this divide and conquer algorithm where we're sorting and splitting in half, sorting and splitting in half. The best way to understand the Quicksort's Big O is to use that Quicksort Viewer app and really kind of get a feeling for it. To actually go in and calculate the Big O or the number of steps is quite difficult. But as you play with it and you can feel the way that it's dividing and conquering, that we have this sort that has all in items that we got to go through, but each time we're only doing half each time. So hopefully you can believe me that this Quicksort has an O in log in speed. So that's what we're going to call this Big O. This is O in log in. So that's a fast sort, and it's a fast in log in. Yes, we have to go through the entire length of the array, but because we're dividing it over and over and over again, that constant division gives us in times log in much faster than in squared. All right, well, I'll see you next time for more data structures and algorithms.